some background. So in the first presentation, I'll give some background on the OpenPOWER ISA and the different compatibility levels, etc. And then in the second presentation, I'm going to go into a specific architecture feature and its implementation, the matrix multiply assist that was introduced on Power 10, you know, and also give a little bit of a background on Power 10 as well. You know, both of these presentations are, you know, condensed versions of sort of a series of talks and documentation from other people. And I've included links to those talks and material in the slides, and I hope Ganesan can make those available to you. So first, you know, I assume this has already happened, but if just in case it hasn't, right? You know, the OpenPOWER is free for academic members, right? So if you're interested in this stuff, you know, go to the OpenPOWER Foundation and join up. So for OpenPOWER ISA, like I said, there is some material that I derived from. So let me dive in here first with a little bit of history. So the first commercial power products started showing up in the 90s, and that's the, you know, train of power systems, you know, that we use in servers. But actually, its history goes back quite a ways before that. So actually, I think even though there were other projects even in the 60s, most people, you know, will say that the beginnings of RISC and power architecture came in the 70s when IBM actually pursued a telephone switch, you know, for AT&T back then, and that telephone switch was calculated to need 4 times the performance that the then, you know, IBM available systems could provide. And you know, John Cock, you know, the father of RISC, you know, had come to the conclusion that a way to you know, create a very efficient processor was to, and you know, kind of go away from the microcode approach that was very common, right, and leads to an explosion of primitive instructions, and have a simpler set of instructions as a foundation, and then, you know, rely on compilers to do optimization against that code. Interestingly enough, as with many other architectural innovations, it turned out that some of the benefits that were had with this hardware-software combination could actually be translated back even to RISC processors, and you know, that sometimes happens. But power is still, and RISC is still a, you know, a very competitive architectural foundation. But it hasn't completely displaced the complex instruction set computers as you know, people thought in the beginning. I certainly personally, when I was in graduate school, I thought it was obvious that RISC processors were going to take over, but actually these you know, compiler effects, as well as you know, when you look inside a CISC microprocessor these days, you actually find a RISC core. So that embedding also, you know, made them less different than it looked like in the very beginning. So that telephone switch project actually got cancelled, but the ideas stayed alive in IBM research. There was a project called Cheetah, followed by a project called America, where actually, you know, prototypes were built, and then it led to the IBM PCRT and eventually to RIOS 1, which is on this chart, is the power, the first power processor, and then things kind of took off from there. As you can see in the chart, right, there was there's not just the server architecture, there's also PowerPC, which was used by Motorola, and mostly for networking and automotive applications, and then also jointly by Motorola, Apple, and IBM in various Apple products. And there was a embedded flavor of that primarily Motorola and later Freescale pursued, and a branch of that architecture that sort of merged back into the server architecture.
Sorry to interrupt, Peter. Just a second. Hello, everyone. Like the session, Zoom link for this Sparsity session is a bit different, and we have shared this over email as well. Mark, if you can hear me, like, can you join using that link?
Yeah, I don't think I received that link. That's why I joined back into this one. I just got your email. Okay. Yep.
Yep. All right. Okay. Thanks, Peter. You can continue.
No problem. And in general here, if people also, if you have questions or comments, please break in. So that is a bit of history of the power architecture. Right now we are on version 3.1, and a few years ago we opened up the power architecture, making it possible for people to build implementations of power architecture that do not require paying royalties, and the architecture is managed under the Linux Foundation. The way it's managed is fairly similar to for example, how RISC-V is managed. The most recent version of the architecture is 3.1, and there's a link to that also in this slide deck. So you do see that over the years, the number of instructions in the architecture has grown, considerably, right? From just over 200 in the first power processor, and less than that in those earlier prototypes, to over 1400 currently. And actually, when we look at the matrix multiply assist later on, you'll see some examples of how that proliferation occurs. So it's still a reduced instruction set in the sense that it is based on instructions that operate on registers, right, rather than more complex things that operate on memory and are implemented with microcode. But it's not reduced in the sense of a small number of instructions. So when we talk about an architecture, of course one has to be specific of what it means to be compliant to the architecture, right? So there's always this kind of stress field that you navigate, where on the one hand you want to make sure that you enable architectural innovation, and at the same time you want to make sure that you maintain architectural integrity, so that if somebody has an implementation of the power architecture and you run an operating system or a compiler or something that purports to be for that architecture, you expect things to work, right? So we also had the goal of making sure that you wouldn't be forced to implement all those 1419 instructions for every version of the Power architecture. So there is a hierarchy here. The simplest compliant version of the architecture is 129 instructions, and that's the scalar fixed point subset on top here. You know, you'll see an FPGA based implementation. You probably already have seen it, microwatt that implements this. There is the scalar fixed point and floating point subset, which primarily adds the floating point functionality and grows it to 214 instructions. The next set that where you can have a compliance level is the Linux subset, and that adds a substantial number of instructions, primarily because the Linux subset actually has a dependence on the vector instructions as well. So with the vector instructions, there's a vector register file and wider load store data paths that are leveraged in the in the Linux kernel. So it's not so easy to separate out those vector registers from the overall Linux subset, but that does make the Linux subset somewhat unwieldy. And then the next one is the instructions that you would need for an implementation that can run the AIX operating system, and finally the full ISA that adds a number of features that are optional at the other levels. So here is a little bit more detail. I'm not going to go over all of this, but just to kind of give you an idea what is in these different levels. So the scalar fixed point subset is pretty much what you would expect for a basic RISC microprocessor. The floating point also is fairly straightforward, right? Adding the floating point instructions. The Linux subset, as I just explained, adds these SIMD instruction, VMX, VSX instructions. It requires support for 64-bit mode, also little endian, right? The architecture itself for Power is bi-endian. We support both little endian and big endian implementations, but the Linux has really made the switch over to little endian some years ago. So that is required. And then there's some things that have to do with hypervisor functionality and address translation. So there is a radix translation supported by Linux, and the LPAR is the logical partitions that we use on the Power architecture. So if we go to the AIX subset, there are some things in there that you probably really would associate with business computing, like decimal float, but also some things that that have to do with maybe more HPC type functionality. Actually, within the AIX subset is a 128-bit quad precision float format. String type instructions, load store string instructions. Some more things that are specific to optimizations in AIX for address translation, a broadcast TLBIE, and other translation related things. And for AIX, big endian support is required, and because it's a superset, you're actually you're expected to have a bi-endian support, but for AIX itself, it relies on a big endian functionality. And then finally, there is a set of optional features that are a variety of optimizations that the compiler will understand, might not always be present, right? So so it'll only generate code for those if they're known to be present in an implementation, right? So you can choose an implementation at each of these levels. Now, the one thing that this chart does not yet address is this question of flexibility, right, and innovation. So you want to have clearly defined compliance levels, so that somebody who builds a compliant architecture at a certain level, that people who use that implementation can actually rely on the software to work. But you do also want to have the freedom for architectural innovation and exploration. And so that leads me to the box here on top. So there is one opcode 22 behind which there is an opcode space that can be used for these customized, where people can introduce their own custom instructions in implementations of the Power architecture that are still compliant. Some examples of work that are going on is, for example, a different variable length vector approach to vector instructions. That is one of the more active things there. And of course, even though this allows custom implementations of various things, for the integrity of the architecture, people are strongly encouraged to bring their innovations once they're deemed to be successful to the architecture committee, right, for adoption into the architecture in a future version. So the hope is that the architecture there will continue to grow, but grow in a way that maintains architectural integrity. So then in this deck, and I'm going to rush in about 5 minutes through the next set of slides. I do have some links in here to open source implementations of the Power architecture cores that can be leveraged, right, to create your own compliant versions, as well as a couple cores here that need a little bit of work to get to full compliance. I'm including them here primarily for reference, so I'm going to speed through this at a maybe a higher pace than is reasonable, but I thought you might like to have it for reference. So the first one of these, and I think you here have heard more about it in this class, is microwatt, right? It implies that it implements, that smallest subset of the instruction set architecture. I think it's a very elegant core. It's nice for educational purposes, and certainly because it is so small, right? When performance isn't your biggest consideration, when you just need a very small compliant core, this is a great one to use. It's quite an active project, right? I again looked at the project this morning, and I see that there are continued contributions. So it's a single issue architecture pipeline that's maybe a little bit deeper than your simplest risk pipeline that you might find in a Hennessy Patterson architecture book or something like that. There's a few extra stages in there to make the frequency a bit higher. But basically a standard pipeline, and it's very, very small. So the units here are lookup tables, which in an FPGA is a little, typically 3 or 6 input generic logic function that is used as a basic building blocks to create things. And this here gives you an idea of the activity of the project. This is actually a little bit old, but like I mentioned, I looked again this morning, and the project continues to be active. The next core that I wanted to point out to you is there's actually 2 cores in the A2 processor family. These were used in systems like Blue Gene supercomputer, and there is also an A2O core that was fully implemented and realized, but not commercialized. This is A2I, and like I mentioned, it was used in Blue Gene Q. It's a 4-way threaded core and 2 wide issue, but it's in order, and it's a very efficient core, and here you see actually an SoC that was built with a number of these A2I cores, as well as a bunch of network related functionality. So this is a different chip than the Blue Gene chip, and an example of an SoC that was put together. It does need sorry, and there is an FPGA implementation of this as well that you can freely access, and it does require a little bit more work, especially in the translation area, to make the core compliant. But I think this is actually not a huge effort that would be required. And then another core is A2O. For those who care about what language the core is written in, the first one is in VHDL, which is broadly used within IBM for processor design. The second one, A2O, is actually written in Verilog. So if you're looking for a core written in Verilog, this might be of interest. This is also, I mentioned in the beginning, there was this embedded branch, right, of the power architecture. This is a book 3E, just like A2I, and therefore, needs the same kind of translation related updates to make the core compliant. This one is out of order and has more sophisticated branch prediction, and is two-way simultaneous multi-threaded versus 4-way threaded for the other one. I'm not going to go through the details here. Also, there is an FPGA implementation. I think it had to be cut down a little bit in terms of cache size, etc., to make it fit. But there is one, and like I mentioned, it would need similar updates as the other core to make it architecturally compliant. A bunch of this work was done by interns in IBM, and I included a bunch of links here to talks and other material in case you're interested in more detail about those cores. So if there's questions about this part, I'll take that now. And if there are no questions, then I'll switch to the second half of my presentation. Oops. Just 1 second. It's a little. Do you see something that says Power 10 and MMA now?